All right, ladies and gentlemen, you are listening to our lecture on modern atomic theory. This lecture should immediately follow the discussions of historical atomic theory, which we've had in class. The purpose of the lecture is to understand how our historical models of the atom were insufficient to explain all of the experiments and phenomena which we observed in the earlier 20th century and beyond. So, let's go ahead and get started here. Back at the beginning of the 20th century, with our development of our model of the atom that we kind of came to from our historical atomic theory discussion, scientists thought that we had pretty much progressed to an understanding of the atom that was more or less complete, with a couple of small exceptions. And as it turns out, those exceptions that we hadn't quite yet figured out turned out to be much, much bigger deals than we initially thought that they were going to be. We had this idea that we pretty much knew everything there was to know about the atom, but a couple of experiments seemed to contradict our predictions based upon our model of the atom, and we needed to find a new way of describing not just the atom, but really fundamentally the entire world of physics from these observations and experiments. So we're going to kind of, now that we've developed that model atom, pretty much just throw it out and start with a brand new understanding of how the world actually works. The first of these experiments that led us to believe that our model atom was insufficient to describe the actual behavior of real matter was an experiment done by Max Planck back in 1900 about what he called black body radiation. This is the type of radiation given off by essentially anything which has a temperature. If you can imagine thinking about like a toaster oven, that toaster oven, as it heats up, it starts to glow. And as those little filaments inside the toaster oven glow, they give off radiation in the form of both infrared radiation, that is heat, but also visible radiation, if you kind of look at them kind of glowing red hot. And as it turns out, this is a fundamental property of all matter. All matter radiates energy into its surroundings based upon its temperature. And Planck had made this prediction based upon our classical understanding of how the world works, that if you heated up an object as it radiated that heat into the surroundings, you should be able to see it radiate off or absorb, going the other direction, fundamentally any different amount of energy. But as it turns out, that's not how the real world worked. Max Planck observed, in fact, that the radiation emitted by those objects heated to incandescence was only emitted in certain whole number multiples of a quantity of energy equivalent to Planck's constant times the frequency. That is to say, every amount of energy was not allowed to be either absorbed or emitted by these hot objects. And from that observation, Planck determined that in fact energy is what we refer to as quantized. That is, there are only specific allowed energy values that allow energy to transfer from place to place. That is, energy comes in specific size packets or chunks. And this was a fundamental departure from our understanding of classical physics, where energy existed on a spectrum where any value was allowed. So we see now that energy is a quantized value. And we took that understanding developed by Planck and his blackbody radiation experiments and took it a step further with a scientist who is probably familiar to all of you. This is Albert Einstein back in 1905. Einstein is probably the most famous physicist of the 20th century from his work on cosmology and the theory of relativity. But this experiment back in 1905 actually earned Einstein a Nobel Prize and would be among the greatest scientific experiments of the 20th century, regardless of all the other stuff that Einstein did with relativity. Einstein was observing what we refer to as the photoelectric effect. The photoelectric effect describes a property of metals in that if you take a surface of a metal and you shine light at that surface, the act of shining light at the surface of the metal causes electrons to be ejected from that surface of the metal. And Einstein had this kind of prediction that if we looked at this photoelectric effect, where you can eject electrons from the surface of the metal, he made a prediction that because the energy carried by light is proportional to its frequency, he thought that if you shone light over a spectrum of different frequencies at the surface of the metal, you should see an increasing number of electrons ejected from that surface as the frequency increases, since higher frequency would imply more energy, and therefore more energy should be able to eject more electrons. So that was what was predicted based upon our classical understanding of how the world works. However, what he in fact observed was very, very different from this. As he shone the light at the surface of the metal, at low frequencies, as it turns out, not just very few, but in fact no electrons were ejected from the surface of that metal. And it wasn't until you reached a certain threshold frequency that you would start to observe those electrons ejected. And furthermore, once you were at that threshold frequency, if you increased the amplitude of the light, that is, you increased the brightness of the light, more and more electrons would be ejected from the surface. But increasing the frequency would not increase the number of ejected electrons. Instead, if you increase the frequency, what ended up happening was you actually ended up increasing the kinetic energy of those electrons as they were ejected. And so essentially what he observed was instead more kind of like a stair-step effect, where increasing the frequency really just increases the number of ejected electrons once you get that threshold point, and then after that threshold, the only way to increase the number of ejected electrons is to increase not the frequency of the light, but the brightness. And from that, Einstein kind of had this realization that in fact what was going on here was that light itself was carrying that energy in unit chunks. That is, light wasn't really carrying energy, again, as a spectrum. It was carrying energy in discrete unit packets of light, and in order to eject that electron, the light had to have sufficient energy contained within that one single packet to actually remove the electron from the nucleus of the from around the nucleus of the atom. And if it didn't meet that threshold, then the electron could not be ejected. That is to say, you couldn't take additive amounts of light to get up to enough energy in order to actually eject the electron. And so from this understanding, what we really see here is that light itself, what had traditionally been treated as a wave-like material, actually kind of had some characteristics of particles as well. We call this a wave-particle duality. That is to say that light exhibits both wave-like behavior, it has a frequency and a wavelength, but also particle-like behavior in that it carries energy as a unit chunk. And we call those unit chunks, those discrete packets of energy, we call those photons. So taken together, Planck's experiment, in which he observed that in fact energy is a quantized value, that is only allowed to be absorbed or emitted in specific whole number chunks of a certain multiple, and that light itself is also quantized, what we really see here is the kind of dawn of what we refer to as the age of quantum mechanics. That is our understanding that continuity of a spectrum isn't really how the world of very, very small things works. Now, moving beyond this, that understanding that light exists as photons is still to us today a kind of familiar idea. But this next experiment is very kind of head-scratching from our perspective, even looking at it today. Back in 1905, a physicist by the name of Louis de Broglie discovered, in fact, that if light, which we had traditionally associated with wave-like behavior, exhibited particle-like characteristics, what if the opposite were also true? That is, what if something we had traditionally treated as a particle, something like an electron, might also exhibit wave-like characteristics? And the way he actually determined this was by looking for wave-like behavior of particles. The wave-like behavior he was looking for was something we call diffraction, which essentially means spreading out into space. If you took physics last year or this year, you might remember in physics looking at what we refer to as a diffraction pattern in some of your lab experiments during the WAVES labs. In particular, if you take a wave, like let's say either a water wave or even like a light wave, and you shine that light at a little slit inside of a piece of paper, on the other side of that slit, the wave exits as what we refer to as a point source wave. That is, it kind of spreads out in all directions. And that's the process we call diffraction. Now, if you imagine that we had not one, but two of those slits, as the light wave passed through there, it would diffract through both of those slits, and it would end up forming this kind of pattern. where you had places where the wave added in such a way that the two crests of the wave added on top of each other, creating a higher amplitude wave. We call that constructive interference. In places where a crest and a trough of the two diffracted waves would overlap each other, canceling each other out and forming what we refer to as destructive interference. And what you end up with then is where the constructive interference occurs, you end up with a higher amplitude wave that is brighter light, and then where the destructive interference occurs, you end up with a position where the value of the wave at that position is 0, and you end up with what we call a node. So when you pass waves through two adjacent slits, they form an alternating pattern of nodes and antinodes that might be familiar from some of your waves labs from last year. And what Desbrosses did back in 1905 was he determined that if you actually used, rather than a beam of light to shine at those two little slits, if instead you used a beam of electrons from a cathode ray tube, you actually ended up getting the exact same diffraction pattern, that alternating pattern of lights and darks, of nodes and antinodes, you would get if you had done it with light. That is to say that electrons appeared to diffract, which is very much a wave-like characteristic. And this discovery was fundamentally game-changing here, because if light itself exhibited particle-like characteristics, then it appeared particles exhibited wave-like characteristics. And Desbrosses came up with this equation here that described the wave-like characteristics of matter with this equation here that said that the wavelength of a particle was equal to Planck's constant divided by the momentum of that particle. And you might think to yourself now wait a minute here, I'm more or less a particle as a human being, I'm a chunk of matter, and I don't exhibit really any observable wave-like characteristics on a daily basis. That is to say, if I walk through a door, I certainly don't diffract noticeably as I pass through that space. So we can come to an understanding about why that might be the case. Let's start by calculating the wavelength of an electron. To calculate the wavelength of an electron, we're going to use our equation here. We're going to take Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. And we're going to divide that by the momentum of that electron, its mass times its velocity. The mass of an electron is 9.11 times 10 to the negative 31st kilograms. And let's say we get that velocity of this electron up to about 10 to the 7th meters per second. Well, that's a reasonable speed for an electron that we've accelerated with like an electric field. And a quick note about the units in this calculation as we go through, so we can make sure everything comes out properly. A joule is the unit equivalent to a kilogram meters squared per second squared. And so if I multiply in Planck's constant joules times seconds, and then divide by the mass of the electron in kilograms times its velocity in meters per second, you'll notice that in looking at my units, kilograms cancel out, and the seconds cancel out. Seconds squared cancels with seconds and seconds. And then I end up with meters squared over meters, which means I end up just with units of meters. And so in making this calculation here, the wavelength of this electron, plugging in my numbers and calculating, turns out to be about 7.27 times 10 to the negative 11th meters, which is a really, really, really short wavelength, right? But here's the trick. That very, very, very short wavelength is, as it turns out, very similar to the distance which separates adjacent ions in something like a crystal of salt, sodium chloride. And as it turns out, the ability to diffract, that diffraction occurs most efficiently when the separation between the slits is more or less about the same wavelength as the wave which is passing through it. Which means electrons, therefore, diffract really, really effectively when you pass a beam of electrons through something like a crystal of sodium chloride. Now, that being said, as a contrast, we could look at calculating the wavelength of me as I pass through the door. If we're looking at a fairly large human here and we want to calculate the wavelength of that fairly large and fairly fast human, that would be equal to Planck's constant, 6.626 times 10 to the negative 34 joule seconds, divided by the mass of that human. Let's just go ahead and, to make numbers easy here, go with a fairly large human mass of 100 kilograms, times the human speed. Let's say we've got a speedy human here who can run at 10 meters per second as they run through that door. And making this division right here, I get a number that comes out to be 6.626 times 10 to the negative 37 meters. And that wavelength of that very large human is incredibly small. That 6.626 times 10 to the 37th meters is like on the order of magnitude of 6 billionths of a billionth of a billionth of a billionth of a meter. And as such, as that human passes through a doorway, that doorway is enormously huge in comparison to the actual size of the wavelength. And therefore, the diffraction that occurs is very, very, very much not observed. As we mentioned again, diffraction happens most effectively when the wavelength is about the same size as the thing that's passing through. So that understanding then is that humans' masses, and really all macroscopic objects' masses, are just so large, which implies their wavelengths of those objects are so incredibly small that we really don't observe the wave-like characteristics of larger scale things. But electrons and protons and neutrons, these things having very, very small masses, might have observable wave-like behavior, which really justifies then why we see this diffraction pattern forming in the experiment. So at this point, we've kind of turned our idea of physics on its ear here, that we had two clearly distinct areas of physics up until this point, one which governed wave-like behavior and one which governed particle-like behavior. But through these three experiments, we've really seen that there's really a blurred line between what really acts as a wave and what really acts as a particle. It seems like we have some sort of dual nature of matter and light, wave-like and particle-like. Now, if that's not confusing enough, we can now move on to something that's really kind of mind-blowing here, and that's going to be another idea that kind of throws out all of our traditional classical physics. This experiment was performed, or really a principle which was predicted by Werner Heisenberg back in the year 1905. And what he did was he essentially took a long-term goal of physicists and said, well, that's a great goal, but it's fundamentally never going to happen because it's impossible. And what physicists wanted to do was really just take the idea that you could make more and more accurate measurements and use those more and more accurate measurements in order to more accurately describe a system which would allow you to make better predictions about what that system will be like in the future. For example, if you think about like playing a game of billiards, if you make calculations of the position and momentum of all the particles in a billiards game, you should be able to predict where all the balls will end up after they collide together and go off in all their different directions. And he just thought maybe the thing that was, or physicists thought maybe the thing that's limiting our ability to make these predictions about large-scale systems like billiards games or even larger-scale systems like weather is just that we haven't measured all of the positions and momentums of all the particles as accurately as we can, and therefore if we just get better at measuring, we'll be better able to predict the future. But Heisenberg came along and said, well, great goal, guys, but we just can't do that. And the best analogy we can use to understand why that's the case is to talk about photography. Imagine you're going through and you're like photographing a soccer game. And during that soccer game, somebody kicks a ball really fast through the air, and you take a picture of that ball as it travels through the air. As that ball travels through the air, if you took a picture of it, it would kind of end up looking like a blur as it moves. And that blur really describes a lot about the motion of that ball. But the Heisenberg uncertainty principle says, well, if we want to describe a system accurately, we need to know not only the motion, that is where they're going, but also where they are. And Heisenberg discovered that it's fundamentally impossible to both know where a thing is and where it is going to an infinite degree of accuracy. That is, the better you know one of those two quantities, position or momentum, the fundamentally less you know about the other. The two are mutually exclusive to know them both at the same time. And if you imagine here, looking at our soccer ball flying through that air, as the soccer ball flies through the air, because it blurred in our picture, we know a lot about where it's going, and we could use that to calculate its momentum. However, because the image is blurred, we can't really tell where exactly it is at that given point. If I wanted to know exactly where it was, I would have to take a much faster picture to kind of freeze it in space. That is, I'd have to use a faster shutter speed on my camera. And if I did that, I could freeze in place where the ball actually was, but then when I looked at that picture, there would be no more blur, which would imply, therefore, I wouldn't actually know where it was going anymore. So the more accurately I know where it is, the less I know about where it's traveling. The more I know about where it's traveling, the less I know exactly where it is. And that invalidated the whole idea of classical physics that we wanted to be able to make more and more accurate measurements, because as it turns out, there are fundamental limits to how accurately you can know both where the things are and where they're going. And because of that, we kind of had to throw out the whole idea of the Bohr model atom with its orbits, because that whole orbital idea was based around kind of an analogy to the solar system, with a nucleus at the center where the sun is, and then those electrons moving around in regular orbits around the outside. Being able to predict their motion and behavior would depend upon being able to know where they were and where they were going. And because we can't do that, the Bohr model atom had to be tossed out. And having tossed out that Bohr model atom, we now moved into a very different way of understanding the world. And our new model atom that replaced the Bohr model is what we call the quantum mechanical model, or the wave mechanical model of atomic theory. And that was proposed by a scientist by the name of Erwin Schrödinger back in 1925. Rather than treating these electrons within the atom as particles in orbits around the nucleus, instead, Schrödinger came at it from a wave perspective. Having recognized that electrons have wave-like characteristics, he instead treated those electrons as essentially standing waves around the atom. And if you remember back from your days on the Waves on the String lab, those standing waves could only form with specific allowed frequencies. That is to say, in physics, if you looked at waves on the string, you can make a standing wave that had half of a wavelength on the string, or if you increase the frequency at which you shook that wave, shook the string, you could increase it to the point where you ended up forming a wave that looks something like this, with an additional node in the center, at a higher frequency. But you couldn't form standing waves with other wavelengths. That is, it had to be some multiple of 1/2 of a wave on the string. You can kind of think of an electron as being the same sort of idea. It's a vibrational frequency which determines the state of energy of that electron. And as treating the electron as a standing wave, we could actually then go about describing it using wave-like characteristics. And that Schrödinger wave-like equation here is very, very different from what you've seen of your normal equations in the past. The equations down here at the bottom of the board, don't worry too much about how terrifying that thing looks. What I really want you to understand about the equation is that it's fundamentally different from other equations you've dealt with in math, in that it doesn't just yield one discrete answer. Instead, it yields a large number of different answers, each of which corresponds to a different energy level of that electron. That is, a different frequency of vibration of that electron as a standing wave. And furthermore, those solutions to the Schrödinger wave function equation don't yield a single answer about where that electron is based upon its energy, but instead it yields an answer as a probability, that is, where it's likely to be. And if all this sounds a little nebulous, a little kind of fuzzy, that should be familiar from a description of electrons you've probably heard of from back in your biology days. That is describing electrons as existing in a nebulous cloud. What we see as the solutions to the Schrödinger wave function equation is not a position of where the electron actually is, but instead a distribution of probabilities for where it's likely to be found. And this image that we have up here right now on the board is what we refer to as the probability distribution of an s orbital, that is, a position in space where we are likely to find those electrons. And these probability distributions, these orbitals, come about as a solution to that Schrödinger wave function equation. And you'll notice here that the probability of finding the electron is very, very high in the center of this diagram right here. This is kind of like a cross-section of a three-dimensional sphere. But then you'll notice outside that central sphere, there's a region in space where you've got kind of a light region, and that light region indicates a place where the probability of finding the electron is very, very low. And then again, around the outside, you've got a higher probability region, and then a lower one, and then a higher one. You've got a series of alternating positions of high and low probability of finding these electrons, which again looks very much like a standing wave. This again shows us our wave-like characteristic of the electron cloud. Now those probability distributions again are what we refer to as orbitals. And those orbitals, those solutions to the Schrödinger wave function equation, come in a variety of different shapes. And we're going to go ahead and fill out this table here describing those solutions to the Schrödinger equation, the shapes of the probability distributions of where we find these electrons. So the first one we've got in here, we refer to this one as an s orbital. That s orbital is spherical in its shape, just like the diagram we looked at up above this table. And if you think about it here, that spherical orbital, if you rotate a sphere in space, it really doesn't change shape at all, which implies there's only really one orientation in space, or one what we call sublevel, of those electrons in our s orbitals. And as it turns out, each of those sublevels of these orbitals can only hold a total of 2 electrons, which implies within any one given s orbital, we can hold a total of 2 electrons spinning in opposite direction of one another. Now, if we take that s orbital, which is the lowest energy orbital for an electron, we could then increase the frequency and thereby increase the energy level of that electron, essentially the same way you did with your waves on a string. So if the s orbital represents essentially the fundamental frequency of that electron, by increasing the frequency of vibration, just like your waves on a string, we would increase the number of nodes present within the wave function and create a more complicated shape orbital. And that's exactly what happens when you increase the energy level of the electron. You end up forming what we call a p orbital, which looks very much like that drawing I just did right there. It's shaped like a dumbbell. That higher energy p orbital dumbbell can be oriented along one of 3 axes, that is the x, y, or z axis. We call those the px, py, or pz suborbitals. And recognizing that if we orient those orbitals along the x, the y, or the z axis, we end up with a total of 3 sublevels, each which can contain 2 electrons spinning in opposite directions. So 3 times 2 electrons gives us a total of 6 electrons, which can be occupied within a p orbital. Again, if you increase the energy level of those electrons further, we can move to a new shape, a new standing wave. The next standing wave we form is what we refer to as a d orbital. Those d orbitals are taken on one of 2 shapes. They are either shaped like 4-leaf clovers. So there are 4 of them that are shaped like 4-leaf clovers. Or, additionally, you can form a standing wave for a d orbital that's shaped like a dumbbell. It's got kind of like a, we call it a dumbbell with a donut. It's got kind of like a torus shape around the waist there. So we have one, we'll call it a dumbbell with a donut. And you can kind of see a pattern developing here. We had 1 s orbital, we have 3 suborbitals for the p orbital, and now we've moved up to 4 4-leaf clovers and 1 dumbbell with a donut, which gives us a total of 5 sublevels for our d orbitals. And that gives us now a total of 10 electrons within a fully filled d orbital. And last but not least, if we increase the frequency yet again to a higher energy state, we form what we call an f orbital. Those f orbitals are shaped either like 8-leaf clovers. So we've got 4 of those. So we have 4 8-leaf clovers. And then we also end up with 3 of them. They're shaped like a dumbbell with 2 hula hoops. So we'll call it a dumbbell with a double donut. So 3 dumbbells with double donuts. And again, following our same pattern, we make a prediction that within the f orbital, we end up with 7 sublevels for a total of 14 electrons held within that f orbital. So again, all these orbitals are the solutions to the Schrödinger wave function equation, describing the probability of where we are likely to find these electrons. Now, here on this next slide is a artistic representation of kind of these shapes of those orbitals. We've got the s, p, d, and f orbitals there. And you'll notice on the far right-hand side over here, we've kind of superimposed those orbitals on top of one another. And in doing so, we end up with these different shapes, and you'll notice that those suborbitals kind of minimize the overlap between those orbitals, which makes logical sense because, remember, these are all electrons which have negative charge. And negative charges repel other negative charges, which would imply to minimize the repulsive force and thereby minimize the potential energy of these electrons, we should seek to minimize the overlap of the orbitals. So there's a kind of a representation of what these things look like. And again, these are not the actual shapes of the electrons. These are the shapes of the regions in space where we are likely to find those electrons as solved as solutions to the Schrödinger wave function equation. Now, that kind of brings us to a nice stopping point at this point right here in our lecture. We're going to break up this lecture into 2 distinct parts here. So this lecture will continue to the kind of what we call a electron configuration, that is the product of the Schrodinger wave function equation, and we'll kind of discuss this one in our next lecture on modern atomic theory. So thanks for listening.